So we now begin the first of our two-part video series on wave properties. So we'll start by asking the question, how does energy move through space? How is it that energy can move from one point in space to another? Well, we'll start by taking a look at the way we already know about, which is via particles. Moving particles have kinetic energy. When a particle moves through space, it carries energy with it. Now, these particles that carry energy can be macroscopic, that is, they can be big enough to see with our naked eye, but very often these particles can be microscopic, that is, too small to see with the naked eye. In the next slide, we'll take a look at some examples. So in this slide and the next, we'll take a look at some examples of energy transfer via particles. And we'll start by taking a look at energy transfer, on a macroscopic level. So I'll use an example which I think many of you will be able to relate to, and that is the example of a snowball fight. If you've ever been involved in a snowball fight, then you know very well that a snowball that moves through space, what we consider a macroscopic particle, really consisting of a whole slew of microscopic particles, that as this snowball moves through space, it carries energy with it. And you know that when that snowball hits your body, if it hits your face, it's going to transfer energy to your face and do some work on it. So very often the transfer of energy by macroscopic objects is pretty obvious and pretty easy to see. Not always the case on a microscopic level. So when energy is transferred via space through microscopic particles, we may not be able to see the energy transfer by the particles themselves, individually, but we may be able to see the effect of a large number of particles transferring energy through space. And this is what I am going to attempt to show you in the next slide, where we take a look at what I call the air-zuka.
All right, so folks, we said that one way in which energy can get transferred from one point in space to another is via particles. That when particles move from one point in space to another, they can carry kinetic energy with them. Now, particles can be macroscopic, that is, large enough that we can see with our naked eye, but particles can also be microscopic. They can be very difficult or nearly impossible for us to see with our naked eye. But even in that case, these particles can carry or transfer kinetic energy from one point in space to another. So I'm going to try to demonstrate that for you with this air-zuka here. And this air-zuka, I filled it up with some smoke, really some tiny glycerin particles. And you see the candle in front of you. And to show you that these particles carry kinetic energy with them, I'm going to try to get that kinetic energy of these smoke particles to actually cause the candle to go out. So let me pull this up, aim it, and we are about to witness the microscopic transfer of kinetic energy via particles.
All right, so we've seen that one of the ways in which energy can be transferred from one point in space to another is via particles, via matter. But there's another way, and that is in the form of waves. Waves can make energy move between 2 points in space without making the matter move between those same 2 points in space. So we have another independent way in which energy can be transferred through space, a way of transferring energy without transferring matter itself. This is in the form of waves. In this simulation, we can create waves that will travel along a string. What I'd like to show you first is how we can actually create a wave by disturbing the medium. And you'll see here that one end of the string is attached to this wrench, and you'll notice that if I move the wrench up and down,
that I can create a wave. What I want you to notice is that the wave and the energy travel from left to right. You see the wave pulse traveling from left to right. Let me shake this again. But the actual particles of the medium simply move up and down. This is an example of a transverse wave because the particles actually move in a direction that is transverse or perpendicular to the direction that the wave and therefore the energy travels. Now we see that if I disturb the medium a single time by moving this wrench up and down, then you see that we would create a wave pulse which will travel from left to right. Conversely, I could actually disturb the medium continuously. I'm going to hit this oscillate feature here, and you'll see that now the medium is being continuously disturbed, in which case we have this traveling wave, okay, which travels from left to right. So we have a whole series of wave pulses.
So let's take a look at some examples of energy transfer by waves. And in this slide and the next, we'll take a look at the radiometer that is exposed to a bright light source. So I think this is a really great example because you can infer that the energy transfer cannot take place by particles. When we expose the radiometer panes to a bright light source, they will start to move. And because these radiometer panes are surrounded by a glass bulb, there is no way that kinetic energy could get transferred to them by particles. Let's take a look.
So in this video, I'm going to demonstrate for you the radiometer that is acted upon by the bright light source. So on your left-hand side of the screen over here, you see a bright light source. On the right-hand side of your screen over here is the radiometer. And it's a little bit dark right now. We'll get a better shot of it once it's exposed to some light. So you'll notice that we have a shield here which is preventing light from actually striking the radiometer panes. So when we get a better look at the radiometer panes, okay, now you can see as we're zooming in on them, you notice that they are not moving. They have no kinetic energy right now. Once we expose them to the bright light source, however, okay, you should see them start to move. So the question is, okay, let's pull up the screen. So we see all of a sudden these radiometer panes start to move. Obviously, if they are moving, okay, they possess kinetic energy. Where did this kinetic energy come from? Well, it came from the bright light source itself. But how is that energy being transferred? Well, it's not being transferred in the form of traditional particles with mass because that glass bulb is preventing any particles with mass from getting through to the radiometer panes. Okay, so where is that energy coming from? Okay, where is the kinetic energy of those radiometer panes coming from if it's not coming from particles? Well, in this case, it's coming in the form of waves. Okay, that is the light waves themselves which travel through space and carry energy with them.
So another example that I think very nicely illustrates the energy transfer via waves as opposed to particles is the motion of an object on a wavy lake. And I think this is an example that many of you will be able to relate to if you've ever been in a lake as a water wave passes by you, or I should say underneath you. So if you take a look at the right-hand portion of your screen, if you look at the buoy over there, you see that as the wave passes underneath the buoy, look at the motion of the buoy. The buoy moves up and down, but it does not move horizontally along with the wave. So clearly there is motion, there is wave motion, there is energy being transferred, but okay, the matter is not being transferred along with it. The buoy and the water particles are moving up and down, okay, as opposed to horizontally along with the wave and energy transfer. So we see that waves become a means of transferring energy through space And as we know from our experience in life, there are many different types of waves that exist. But what we may not know is that all waves can be classified as either mechanical waves or electromagnetic waves. That is, all waves fit into one of these two classes of waves. So what is it that makes a mechanical wave different from an electromagnetic wave? Well, it turns out that mechanical waves, as the name would suggest, require a medium for travel, okay? A medium that they must travel through, a medium for propagation. Electromagnetic waves do not require a medium, although electromagnetic waves can travel through certain media. Take the example of the sunlight that may be allowing you to see inside your room right now, depending on what time of day you're actually viewing this presentation. That sunlight started its journey to your room about 8 minutes ago, 93 million miles away at the surface of the sun. So it traveled most of its journey through empty space. Okay, but you know that it had to travel that last little portion of its journey, okay, through the glass window to be able to enter your room and ultimately your eye. So light, an electromagnetic wave, traveled most of its journey through empty space, but it did travel that last little portion. Once it hits the Earth's atmosphere, okay, it had to travel through matter. So we're going to take a look at a nice example, okay, to see the difference between mechanical waves and electromagnetic waves with this demonstration of the bell and the light inside of a vacuum chamber, where we'll see that mechanical waves, like sound, must have a medium in which to travel. So we will look at a few more examples in this slide of both mechanical waves and electromagnetic waves. And when we talk about these mechanical waves, like water waves, remember that all mechanical waves require a medium, so we will identify the medium for each of these examples. So obviously water waves must travel through water. Sound, as we saw in the demonstration, requires a medium as well. Okay, you saw what happened when we got rid of the medium in the vacuum chamber. Typically, we hear sound waves traveling through air, but sound waves can travel through water or steel just as easily. We'll do a unit on sound later in this course and talk in greater detail about that. Now, whereas waves created by instruments are generally heard by us as sound waves, okay, they have to be created in some other medium. Typically, they're created by a vibrating object in another medium. So, for example, a vibrating guitar string can create a wave which can then interact with the air and create a sound wave. Or if we talk about a wave created in a coil spring, okay, the medium being the coil spring, this is something that we do in the lab typically. When it comes to electromagnetic waves, remember that electromagnetic waves do not require a medium to travel. Now, obviously, the electromagnetic wave we're most familiar with is that of light. Okay, but later on this semester, when we talk about optics in greater detail, we will see that there's many other frequencies of electromagnetic waves, like radio waves, X-rays, and microwaves, which we will talk about. And as we say, all electromagnetic waves can travel through empty space, okay, although they can travel through media as well. So in this slide, we'll talk about what is required for a mechanical wave to first get created, and second, for it to propagate in a medium. Well, obviously, there must be some source of disturbance to the medium. Okay, like our friendly tuning fork here. There's going to be some sort of vibrating object, okay, that is going to disturb the medium. Energy is added to the medium in the form of this disturbance. Secondly, and perhaps most obviously, you need a medium that can be disturbed. And lastly, you need some sort of physical connection between the different particles in the medium. So a nice analogy, you can kind of think of the particles in a medium as being connected, okay, by little tiny springs. What is the real connection between the particles in the medium? Well, it's an electromagnetic force, a force between oppositely charged particles that is the real source of the connection between these particles. So while we said that all waves can be classified as either mechanical waves or electromagnetic waves, it turns out that when we talk about mechanical waves specifically, there are subclasses of waves. So how is it that we classify mechanical waves into these subclasses? Mechanical waves are classified according to the direction the medium moves in relation to the direction the energy travels. And you can see here in some of these examples, I'm showing you examples of really three classes of mechanical waves: transverse, surface, and longitudinal waves. And we'll take a look specifically in the next slide to see the relationship between the direction of medium motion or particle motion in the medium versus the direction the energy travels in the medium. So let's look at this phenomenon in greater detail to see how and why mechanical waves get classified as they do. The first class of mechanical waves is what we'll call transverse waves. So in a transverse wave, the medium is displaced in a direction that is perpendicular to the direction the energy travels. So let's look at an example. In this example, we see a transverse wave that is being created on a coil spring. Notice in the example that the hand and therefore the coils in the spring move up and down in the vertical direction, but that the wave and the energy moves from left to right, that is in a horizontal direction. So do you see here how the hand and the particles in the medium are moving perpendicular to the direction in which the wave and the energy are traveling? In the second class of waves, what we call longitudinal waves, in this case the medium moves both parallel and anti-parallel to the direction the energy travels. So once again, we'll take a look at a wave created on a coil spring. Notice in this example here that the hand moves from left to right, okay, in the same direction as the energy travels. First the hand moves to the right, then it moves to the left. So the hand is moving both parallel and anti-parallel. Okay, that is in the same and the opposite direction to the direction the energy travels. This is what is characteristic of a longitudinal wave. And finally, we can talk about surface waves. Okay, in surface waves, the medium moves in a direction that is both parallel and perpendicular to the direction the energy travels. And when you combine these two motions, okay, the elements on the surface move in a nearly circular path. This is a type of wave that would be created in water, okay, not when a wave breaks on the shore, but when the water is deep enough. And if you look here, this is a nice simulation. Take a look at the red particles on the surface of the wave. The wave is traveling from left to right in this diagram, but if you look at the motion of particles in the medium, let's say those red particles, they are moving in a circular path. That is, they are moving both in the same and opposite direction as the direction the energy travels, and perpendicular to the direction the energy travels. When you combine or superimpose these two motions, you end up with this circular motion. So let's take a look at some more examples of the various subclasses of mechanical waves to see how the medium or the particles in the medium move in comparison to the direction that the wave or the energy moves. We'll start here with a sound wave. Okay, and sound waves are longitudinal waves. The particles in the medium, whatever medium that may be, will vibrate or oscillate in a direction that is both parallel and anti-parallel to the direction that the energy or the wave travels. What about a wave on a guitar string? So as you can nicely see in this stroboscopic slow motion video clip, that the wave in the guitar string travels along the string, along the length of the string. But if you take a look at how the particles in the string are oscillating, they're moving perpendicular to the length of the string, perpendicular to the direction that the wave and energy are traveling. That makes this an example of a transverse wave. What about a water wave deep in the ocean? Well, as we saw in the previous slide, when you look at a water wave that is created in a deep water source like the ocean, we see here that there is a circular motion to the particles, okay, to the water particles themselves. Okay, this is what we call a surface wave. Those particles are moving both in the same and opposite direction as the energy travels, as well as perpendicular to the direction the energy travels. And the superposition of these two motions gives us this circular motion. When it comes to earthquakes, there are really two types of waves. There's P waves and S waves. The P wave stands for primary waves. These are the waves that would reach your seismic station first. And if you look at the simulation here, you see that for a P wave, okay, the direction that the energy travels is in the X direction. Okay, take a look at the direction of the medium displacement. When the wave is created, okay, the medium moves, okay, both in the plus X and minus X direction. This makes P waves an example of longitudinal waves, okay, where the medium moves, okay, both parallel and anti-parallel to the direction that the wave or energy travels. The S wave from the earthquake, okay, this stands for secondary wave. These are the waves that travel a little bit slower and reach the seismic station a little bit later than the primary waves. Notice here in the simulation that just like in the case of the P wave, the wave travels in the X direction, so the energy travels in the X direction. But notice here that the particles in the medium are displaced in the Z direction, transverse or perpendicular to the direction the energy travels. So this makes the S wave a transverse wave. And if you look in the bottom picture here, okay, in the freeway collapse here, this is clearly an S wave that is causing, okay, you can see the direction of the energy travel as the crack forms, but you see the medium move, okay, perpendicular to that, okay, as, okay, this unfortunate driver finds out. And when we look at doing the wave at a sporting event, okay, this is only a quasi-wave, because when we talked about the requirements for mechanical wave creation and propagation, I'm not sure that we technically have connection between the different particles in the medium, the particles here being people. But clearly, if you were to classify this, okay, you would say, well, it's a mechanical wave. There's clearly a medium. There's the people. And if you look at the direction the people move, they simply move up and down, whereas the wave travels in a horizontal direction, making this a transverse wave. So in this last example here, I didn't include it in the table because this is light. Light is not a mechanical wave, but it is transverse by nature. So when a light wave travels through a medium, it will make the particles in the medium vibrate in a direction that is perpendicular to the direction that the wave or the energy travels. So we now want to turn our attention to the task of describing waves in a quantitative way. And I want to start out by making this distinction between a wave function and a waveform. Because as we'll see, when we represent waves graphically, okay, the shape of these graphs may look very similar, yet they represent two very different things. So starting with a wave function, okay, a wave function can represent the displacement, okay, of one particle in a medium, okay, at, let's say, one specific position x, where we let x have a constant value. So we're looking at one particle at various times t. How does that particle move in time? And if we were to make a graph of that, okay, the motion of the particle in time, okay, it would take this wave-looking shape. Okay, so I want you to notice here that y represents the position of the particle, and on our horizontal axis we're graphing time. So we're looking at the position of the particle as a function of time. Let's contrast that with a waveform. Okay, the waveform, notice our y-axis is the same, but our horizontal axis shows a spatial coordinate x. What our waveform shows is the snapshot of a wave, okay, in space at a particular point in time. Okay, the waveform defines the geometric curve or the shape of the wave at any given time. It's a spatial representation of the wave. So notice here that our generalized wave function y of x of t, now we're looking at many values of x, many different particles in the medium, but we're looking at one particular point in time. So this gives us a spatial representation of a wave. This is what we call a waveform. Now you see here why I'm making a point of this. Okay, while both of these graphs are representing two very different phenomena, okay, the shape of the graphs look very similar. So a word of caution here from our wave function friend that says, watch out, I look a lot like my cousin Wally waveform. So you'll notice here that the wave function, the horizontal axis, is really a measure of time, okay, whereas for the waveform, the horizontal axis is described by a position x. Okay, the shape of the wave function of the waveform may look similar, okay, but we're graphing two very different quantities on that horizontal axis. So when it comes to the task of describing waves, I want you to think back to the beginning of your physics career in your course on mechanics, where you were asked to describe the motion of objects. And recall there we said that in order to describe the motion of objects, whether we're talking about objects moving in one dimensions or two dimensions, we introduced a set of kinematic variables that would allow us to do so. Okay, these variables, you recall, were position, velocity, and acceleration. In the same way, okay, in order to describe the motion of a wave, we will describe a set of variables, okay, that will allow us to do so, that will allow us to describe the motion of a wave. So let's introduce these basic variables describing wave motion. And you'll notice what you see here on the screen, and I was careful to make a point of this on the previous slide. This is a waveform. So this shows you a spatial representation of a wave. You can imagine, for example, that this represents a wave traveling on a string, for example. You're seeing a snapshot, a picture of that wave in space at one point in time. So on this waveform, okay, we will start by identifying what we call the crests, or the wave peaks or high points on the wave. So here I'm showing you two successive wave crests on the wave. Okay, similarly, we can talk about the wave troughs as being the valleys or the low points on the wave. So here are two successive wave troughs. When we talk about the wavelength of a wave, and we use this Greek symbol lambda to represent the wavelength, we're really talking about the distance between two adjacent crests on the wave or two adjacent troughs. So for example here, this represents one wavelength, the distance between two adjacent crests. Okay, here this distance also represents one wavelength, the distance between two adjacent troughs. Okay, you can see here on this representation, okay, the same information. When we talk about the amplitude of a wave, we're talking about the distance between the midpoint of the wave and either a crest or a trough. So, for example, here you see the distance between the midpoint of the wave, which would represent the equilibrium position of the wave, and a high point, okay, a crest. That distance is the amplitude. And we'll talk more about this later. Okay, but the amplitude is a measure of the energy that the wave carries. You can imagine that to create a large amplitude wave, okay, a wave with a high wave crest, a large wave crest, this would require you to add a lot of energy to the medium. Okay, what happens to that energy you add to the medium? Well, it ends up, okay, in the form of the wave. So a large amplitude wave, as we will see later, represents a wave carrying a lot of energy. So in this slide, we will continue describing basic wave variables that we can use to, okay, describe the motion of a wave. And I want you to notice here, okay, in the diagram, we no longer have a wave form. Okay, we no longer have a spatial representation of a wave. We're now looking at the wave function. Notice on your horizontal axis, we have time plotted. So what we're showing here is the motion of a single particle in a medium at a specific position x. Okay, but we're showing, okay, how that particle moves in time. So time becomes a variable. So when we talk about the period of a wave, which we'll symbolize with a capital T, we're talking about the amount of time required for one complete wave to pass a given point in space. So imagine you are standing at a given point in space watching, okay, a traveling wave go by you, okay, whether it's a water wave or a wave on a string. Okay, the period would be the amount of time it would take, okay, between seeing one crest of a wave and seeing the next successive crest. Okay, so the amount of time for one complete wave to pass by your eye. So in our graph here, you see that this, what looks like this horizontal distance is really a measure of time because we have time plotted on our horizontal axis. When we talk about the frequency of a wave, we're really talking about the number of complete waves passing a given point in space per unit time. So once again, if you are standing at a specific point in space watching waves pass by you, if you were to count 2 waves passing by you in a time of 1 second, okay, then we would say that the frequency would be 2 waves per second. Okay, how many complete waves pass a given point in space per unit time? When we talk about the speed of a wave, we're talking about a measure of how fast the wave disturbance propagates through the medium. And remember, what is it that waves do? Waves are a means of carrying energy, okay, from one point in space to another. So as that wave propagates through the medium, it carries energy with it. So you can also think of the wave speed as being a measure of how fast the energy travels in the medium. We will now very quickly review the SI units for the variables that we just introduced. So when it comes to wavelength, as the name would imply, we're talking about a length, so the SI unit would be the meter, okay, in the MKS subsystem of units. Amplitude, remember, is a measure of the wave height on the waveform. It too would be measured in meters. Period is a measure of time. Same as when we talked about uniform circular motion. We said the period is the amount of time it takes for an object to make a complete circle. Here, period, amount of time it takes for a complete wave to pass a given point in space. It's a measure of time. Frequency is really a reciprocal of time, right? The number of waves per unit time. We call this a hertz, okay, just as we did when we talked about uniform circular motion. And speed, everybody knows that, would be measured in meters per second in the MKS, okay, subsystem of SI units. Relationship between period and frequency, you should already know this. Okay, they're reciprocals of each other. Just want to make a point here that the frequency f is what we call the characteristic frequency, as opposed to omega, which is an angular frequency. Okay, and these two frequencies are related to each other by this factor of 2 pi. So we'll take a look at this wave simulator to see the difference between a wave pulse and a wave train. Starting out with the wave pulse, a wave pulse is what is created when there is a single disturbance to the medium. So as you see here, when this oscillator moves up and down one time, it creates a wave pulse which travels down the medium. In order to create a wave train or continuous traveling wave, we need to continuously disturb the medium. So what we'll show here is that the oscillator, okay, will continuously disturb this medium, in which case we have a traveling wave or wave train. So how do we describe a wave pulse that travels in a given medium at a speed v? Let's start by saying that the wave pulse takes on a certain shape in space, okay, so that the waveform of the wave pulse can be described as a function f of x at a specific point in time. Now, to get the wave pulse to travel in time, we need to incorporate the time dependence into our generalized wave function. For a wave pulse traveling to the right, we can say that for a wave pulse described by the waveform f of x, the wave function will be described by the function f of x minus vt. That is, replacing x with the expression x minus vt gives the wave motion to the right. In comparing the top picture to the bottom picture, you can see that the wave pulse at time 0 in the top picture has traveled a distance vt to the right in a time t. Okay, that's what the bottom picture is representing. Similarly, to describe a wave pulse that travels to the left, we can say that the wave function must be a function of the expression x plus vt. This will become a little clearer when we look at a specific problem in the next slide. So we will now look at an example of a one-dimensional traveling wave pulse. So in this example, we're told that at time 0, a one-dimensional transverse wave pulse on a string is described by this function y equals 5 over x squared plus 2, where x and y are measured in meters. Okay, so what we're giving here is we're given the waveform, okay, a snapshot of what that wave looks like, okay, in two-dimensional space at time 0, at a specific point in time. We're asked to write the function, the wave function, okay, y of xt, that describes this wave, okay, if it is first of all traveling in the positive x direction with a speed of 2 meters per second. Now recall what we said on the last slide, that to take a wave pulse and to give it motion in the positive x direction, okay, we need to replace x with the expression x minus vt, okay, where v represents the wave speed. So here, by doing that, by replacing x in our wave form, okay, with the expression x minus the speed 2t, okay, we now take a wave pulse at one instant in time and we give it motion in the positive x direction, okay, to the right in the conventional coordinate system. If we wanted to similarly describe, okay, or make that wave pulse travel in the negative x direction at a speed of 4 meters per second, okay, recall what we said, that a pulse traveling in the negative x direction must be a function of x plus vt. So taking our waveform at a specific time and replacing the x with the expression x plus the speed of 4 times t now gives our wave pulse, okay, motion in the negative x direction. All right, so in part 3 of this question, we are asked to plot the waveform, okay, for the case of the wave traveling in the positive x direction, okay, at these two particular times, at time 0 and 2 seconds later. And we want to then verify that these plots are consistent with the pulse speed of 2 meters per second. So we're going to do this the old-fashioned way here. We're just going to plot some points here. So when we look at, okay, the specific time 0, our wave function takes on the form, okay, becomes this waveform, okay, 5 over x squared plus 2, and we're just going to arbitrarily plot some points. So we'll look at some values of x and plug it into the function and see what our corresponding y values are. And we will do the same when we look at the waveform at a time of 2 seconds. Okay, so we'll plug in a time of 2 for t rather than 0. And we will do the same. We will plot some points. And then we are simply going to, okay, sketch these points, which I'm showing you here on the graph. So you see the brown graph represents, okay, our waveform at time 0. The blue graph represents our waveform, okay, at a time 2 seconds later. And here you can clearly see what has happened, okay, that in a time of 2 seconds, the waveform has shifted to the right, okay, a distance of 4 meters. Does that make sense? Well, yes. Okay, if our wave is traveling at a speed of 2 meters per second for a time of 2 seconds, then we would expect that, okay, that entire pulse has shifted to the right a distance of 4 meters. So now we turn our attention from the case of a one-dimensional traveling wave pulse to that of a one-dimensional traveling wave train, a continuous traveling wave. We'll look specifically at a certain class of traveling waves that can be described by a sinusoidal function. So how is a sinusoidal wave created? Okay, it's created when the object that is disturbing the medium, okay, that is creating the wave itself, is a simple harmonic oscillator. Okay, so when that simple harmonic oscillator disturbs the medium, it creates a sinusoidal traveling wave, okay, having a general form that can be described by this sinusoidal function. So what we're showing you here is a wave function, okay, y, okay, of xt being equal to a times the sine of the argument being kx plus or minus omega t plus phi. Okay, and I want to show you here, okay, that if we start with the simple harmonic oscillator itself, so what I'm showing you in red here is an expression. It's the equation of motion of the simple harmonic oscillator. Okay, and you see on the graph here, we're looking specifically at a particle that is moving on the end of the spring, a point mass moving on the end of a spring. And imagine taking that simple harmonic oscillator that can only move in one dimension, allowing it to interact with the medium. Okay, you can see here that instead of looking at the oscillator itself, we now look at the wave it creates in the medium. Okay, the energy or wave now travels in 2 dimensions. So do you see here that when we compare these two expressions, the wave function to the equation of motion for the oscillator, okay, the difference we see here is this kx factor. Okay, we add in the kx factor and the equation of motion, okay, for our oscillator showing the position of one particle in the medium as a function of time, okay, that equation of motion now becomes a wave function showing all the positions of the point x in the medium as a function of time. Okay, so our equation of motion, okay, showing just one point in the medium as a function of time, okay, when we add in this factor kx, okay, we are now showing all points x in the medium, okay, as a function of time. So this is now a wave function. So if we want to describe these, okay, these variables in this generalized wave function here, okay, understanding what these constants mean here, we'll take a look at them one at a time, and we'll see what effect does changing these constants have upon the wave itself. Okay, starting with the amplitude A here, okay, we've already said that's really the maximum displacement of a particle in the medium from its equilibrium position. So that would, in the waveform, represent the wave crest or wave height, okay, from the midpoint of the wave. So what effect does changing A have on the wave itself? Okay, well, it basically changes the maximum height of the waveform and the wave function. It stretches the waveform and the wave function vertically in the y direction. That is the effect of changing the amplitude A. Now, this constant k is what we call the angular wave number, and it is related to the wavelength of the wave. Okay, this is just another way of representing, okay, wavelength, so to speak. If the wavelength is a measure of length, then the wave number is a measure of the number of waves per unit length. So you need to memorize this definition, that k, the wave number, is equal to 2 pi over the wavelength. What effect does changing k have on the wave? Well, this simply changes the wavelength of the wave. It stretches or compresses the waveform horizontally in x. Okay, so when you change k, you're going to stretch that waveform in the x direction. In other words, you're going to make the wavelength bigger or smaller. We see here that there's an inverse relationship between k and lambda. So, okay, making k bigger is going to make the wavelength smaller. Now, this angular frequency, that's the constant omega, okay, which is related to the characteristic frequency f, okay, by this factor 2 pi. Okay, it's also related to the period here. So this angular frequency is a measure of frequency. What effect does it have upon the wave? Okay, well, it basically changes the frequency of the wave. It stretches or compresses the wave function in time. So when you increase omega, when you increase the frequency of the wave, what you're seeing in this simulation here, okay, you're getting more waves passing a given point in space per unit time. Okay, and finally, the phase constant, phi, okay, what effect does that have on the wave? That changes when the crests and the troughs occur. Okay, it has absolutely no effect on the shape of the wave. It simply shifts the wave function horizontally in time. Okay, it tells you that, okay, your y position of the wave, okay, at time 0, okay, may be different, okay, but it has no effect on the shape of the wave. So we'll now look at a specific example where we will be asked to, okay, write a generalized wave function for a specific sinusoidal traveling wave. In this case, a wave traveling on a rope in the negative x direction, having an amplitude of 5 centimeters, a wavelength of 40 centimeters, a characteristic frequency of 2 hertz, and we're given the set of initial conditions for a wave function. We're told that a specific point in the medium, okay, that when x is 10 centimeters, at time 0, it has a value of 0. We'll see how that initial condition is used to evaluate one of our constants. So, okay, remember we have this expression for the generalized form of a sinusoidal traveling wave, and writing that wave function amounts to finding out what those constants are, okay, k, omega, and phi. So let's start, okay, by trying to evaluate these constants given the information in the problem. So starting with k, the wave number is related to the wavelength. The wavelength is given to us, so we can take this factor 2 pi, divide by the wavelength of 40 centimeters, and we will get our wave number. I'll leave it in the form of pi over 20. Okay. Our angular frequency omega is related to the characteristic frequency by this factor 2 pi. Since the characteristic frequency is given to us, we know omega as well. And here is the generalized form of the wave function. Notice that since this wave is traveling in the negative x direction, okay, then our wave function has a plus sign, okay, here. Okay, it's kx plus omega t. Remember we said that for a wave traveling in the negative direction, it's written with the expression of x plus vt. Okay, so here kx plus omega t. And here we're going to use this set of initial conditions here to figure out the value of our phase constant phi. So when we plug in the value here, and the amplitude is given to us of 5 centimeters, so we know that. That's given. We don't need to evaluate that. We'll figure it out. So we plug in all these constants, okay, A, omega, and K, and this is what our generalized wave function looks like. When we plug in the set of initial conditions, that is when x has a value of 10 at time 0, okay, we now can evaluate this phase constant phi. Okay, and here if the sine of pi over 2 plus phi equals 0, that tells us that phi, okay, this phase constant, must have a value of pi over 2 radians. Okay, once we know phi, we know all 4 of these constants. Okay, we can plug them into our generalized wave function, and we are done. So this brings us to the topic of the all-important wave equation. This all-important wave equation is nothing more than a kinematic equation describing the motion of an object, okay, a wave in our case, traveling at a constant speed, okay, but translated into this new set of variables that we've introduced to describe wave motion. So we're going to quickly derive this equation, and given a wave traveling at a constant speed in an isotropic medium is a medium that looks identical, okay, regardless of the direction you move through it. So when we have a wave traveling in an isotropic medium, we can assume that the wave travels at a constant speed in the medium. Okay, and this equation should look very similar to you, okay, that the kinematic equation used to describe the one-dimensional motion of an object traveling at a constant speed, okay, distance equals rate or speed times time. In our case, remember we said that for a wave, we are going to write this kinematic equation in terms of these new variables that we've introduced to describe wave motion. So a wave that travels a distance of one wavelength in one period, we're going to substitute these values in for distance and time. So we can say that for a traveling wave, it will travel a distance of one wavelength in a time equal to the period of the wave. We'll substitute that in. We will solve for v, okay, wave speed, and then typically we like to represent this wave equation in terms of frequency rather than period. And remember, there's an inverse relationship between the frequency of the wave and the period of the wave. So here we have it. Okay, the wave speed is equal to the wavelength times the frequency. So this equation is simple, okay, but very important in our discussion of waves. So let's now check out a simulation in the next slide to nicely see this relationship between the wavelength of a wave and the frequency of a wave.
All right, so in this simulation, we're going to take a look at the relationship between the wavelength of a wave and the frequency of the wave. So you'll notice here in this initial setup, we have this wave on a string, which is being generated by this oscillator over here on the left. and we're going to put it in the slow motion mode, and I'm going to pause it, and we're going to measure the wavelength, and you'll see that the wavelength has a value, looks like it's about looks like it's about 7 centimeters long. Okay, that's when the frequency of the wave is about 0.83 hertz. So you can visually take a look at the wavelength as well. Let's see what happens here when we increase the frequency of the wave here. Okay, take a look at what happens to the wavelength. So as the frequency of the oscillator increases, as it makes more oscillations per unit time, okay, you can nicely see what happens to the wavelength. And notice here when I pause it that the wavelength has been reduced from about 7 centimeters here, okay, to about, okay, a little more than one, about 2 centimeters here, the distance between these two crests here. Okay, so we're looking at about 2 centimeters. So you can see that there is an inverse relationship between the wavelength of the wave and the frequency of the wave. As the frequency increases, the wavelength decreases.
So let's look at a simple example, or rather I should say a couple of examples where we can get some practice applying this all-important wave equation. And we'll take a look at the example of radio waves. And I'll ask you, do you ever wonder where those numbers come from on your radio dial? Okay, well, in the case of your AM radio, okay, AM radio signals have frequencies between 550 kilohertz and 1600 kilohertz. And as we will see later, okay, all electromagnetic waves traveling in a vacuum travel with a speed of 3 times 10 to the 8th meters per second. We're asked to find what are the wavelengths of these signals. Well, okay, we have a low frequency and a high frequency signal here, so we really have two problems here. So from our wave equation, the wavelength is given by the wave speed divided by the frequency. So we plug in our wave speed, 3 times 10 to the 8th meters per second. Okay, the low frequency, or 550 kilohertz, when we plug this in and do the number crunching, we get a wavelength of 550 meters. Okay, we'll do the same for the high frequency, and you see that we end up with a wavelength of 190 meters. So a couple things here. Notice that, okay, for AM radio signals, these wavelengths are quite long. Okay, these are on the, these are very long wavelengths. And later on in the course, when we talk about diffraction, we'll see why, AM radio signals, because of their long wavelengths, can diffract or bend around mountain ranges much better than shorter FM waves can. The other thing to note here is that this inverse relationship between wavelength and frequency. Notice that, okay, the lower frequency wave, the 550 kilohertz radio signal, had a much longer wavelength. When we shift our attention to FM frequencies and FM wavelengths, you may have noticed these numbers 88 and 108 on your radio dial. These are in units of megahertz. Okay, so these are much higher frequencies, on the order of 1,000 times higher than those of AM radio signals. So, okay, going through the same calculation, plug using our wave equation to figure out the wavelengths. Okay, we find out that, okay, the 88 megahertz FM signal corresponds to a wavelength of 3.4 meters, and the 108 megahertz signal corresponds to an FM wavelength of 2.8 meters. Notice that FM signals are typically on the order of a few meters, much shorter wavelength signals than AM radio signals. I'll also point out here that when we talk about AM and FM signals, these are not single waves. These are wave packets that are created. And okay, we will also later on talk about the difference between AM, which stands for amplitude modulation, and FM, which stands for a frequency modulated wave.